Dr. Shishler, am I audible?
Yes. Hello, here.
So shall I start?
Yes, if it's up to you.
Okay, thanks a lot, sir. Mr. Uttam, you there?
I'm available, Shashank.
Okay, sir, we are starting now.
Okay.
So, namaskar and a very warm good afternoon to the esteemed guests, distinguished speaker, participants, ladies and gentlemen. My name is Shashank, and alongside me is Mr. Uttam from IT department. And on behalf of SIGRE India and Central Board of Irrigation and Power, it's my honor to welcome all of you to this international tutorial on application guide for partial discharge detection in GIS using UHF or acoustic methods. This event is being organized under the aegis of SIGRE National Committee on D1 on materials and emerging test technologies. We are honored to have with us for opening session Shri A.K. Bhatnagar, Director CBIP and SIGRE India. We also have with us Shri B.P. Muni, National Representative in SCD1 and GMBHEL, and our eminent faculty for today's program, Dr. V. Schechler from Germany and SIGRE. As all of you know that today's session will be a 90-minute session where the Q&A session shall be taken at the last of the presentation. We have requested Dr. Schechler to take all the queries of the participants at the end of the presentation. So you all are requested to kindly keep yourself muted. You can post your queries in the chat box to avoid them from missing, and all the queries shall be taken by our speaker at the end of his presentation. So ladies and gentlemen, SIGRE, as you know, is a unique platform to share experiences. Now, before I invite Shri A.K. Bhatnagar, Director SIGRE India and CBIP for the welcome address, we would like to display a film about SIGRE for the benefits of the participants who are not much familiar with SIGRE. So now I'll request Mr. Uttam to kindly share the SIGRE film, please.
SIGRE, the International Council on Large Electrical Systems, is World Forum for Power System founded on November 22, 1921 at Paris. SIGRE deals with the issues related to the development, operation and management of electric power systems as well as design, construction, maintenance of equipments and plants. Mission of SIGRE is to promote and organize in collaboration with experts from all around the world by sharing knowledge and joining forces to improve the electric power systems of today and tomorrow. It mainly aims on coordination of research, exchange of experience, scientific and technical information on the operation and design of electric power systems. SIGRE is an association that promotes the exchange of latest generation of technical knowledge regarding electricity and bringing innovative ideas to support the industry needs. SIGRE has worldwide network of experts from ministries, generating companies, transmission and system operations, distribution operators, regulators, manufacturers and academies. It has gained international representation in nearly 90 countries through national committees in order to provide opportunities for improvement of services supplied to the society. SIGRE has 16 national committees, 95 member countries, more than 10,000 individuals and more than 1,000 organizational members. SIGRE strategic direction are best use of existing system, unbiased information for all stakeholders, environment and sustainability, and future power systems. The challenges are renewable energy sources, growing environmental requirements, limitations to build new transmission infrastructures, architecture of networks, operation of existing power systems, transmission of large amount of power over long distances, cybersecurity, and intermittency of renewable power generation. SIGRE operates through 16 committees on different subjects having members from various countries. These committees are divided into 4 groups. Group A, Equipment, and the study committees are A1, Rotating electrical machines, A2, Transformers, A3, High voltage equipment. Group B, Technologies, and the study committees are B1, Insulated cables, overhead lines, substations, HVDC and power electronics. B5, Protection and automation. Group C, Systems, and the study committees are C1, System development and economics, System operation and controls, System environmental performance, System technical performance, electricity markets and regulation, distributed system and dispersed generation. Group D, New materials and IT, and the study committees are Materials and emerging test techniques, Information systems and telecommunication. The study committee of SIGRE has about 250 working groups which produce nearly 50 technical brochures per year. The work carried out in SIGRE environment is considered as reference being applied to the development of technical standards. SIGRE develops technical knowledge using 2 main methods: conferencing and meetings, where papers are presented and discussed, and studies carried out by study committees through the work of international working groups on identified industry issues. SIGRE has recently started a series of science and engineering journal. 6 issues have been published in 2015-16. SIGRE has started series of new publications named Green Books. The books on the following subjects are already released: accessories for HV extruded cables, overhead lines, and utility communication network and services. So, why is it especially profitable to join SIGRE activities? Joining a SIGRE working group as an expert always result in a high return for your organization as well as for yourself, all the more so for a young engineer. You become part of a worldwide network of experts with whom you discuss current issues, share international experience, and benchmark your own practices. You are in a position to promote your ideas and weigh on the contents of specifications, recommendations, and future standards. Experts represent all the profiles of the power industry, hence a wealth of opportunities to start cooperation between university and industry, between industry and administration, etc. At a personal level, you are in contact with other cultures, practices, working methods. You acquire knowledge through working and experienced experts. National, international teamwork and practice of technical English enhance your personal development. New generation networks. National Committee of countries like UK, US, Australia, New Zealand, etc. have created a next generation network, NGN, that aims to develop the next generation of power engineering professionals. SIGRE is present in India since 1971. Since its foundation, SIGRE India helps the country to deal with its challenges in the areas of electricity and demonstrates the strength of the Indian power system engineering worldwide. The SIGRE India brings together top experts spread across 16 minor study committees at national level. The dissemination of consolidated knowledge is done through publications and national and international workshops, seminars, symposia, etc. So, get associated with this unique organization and take maximum advantage of this forum for accentuating the knowledge in electric power system.
Thank you everyone for their patient listening. Now, without further delay, may I invite Shri A.K. Bhatnagar ji, Director CBIP and SIGRE India, to deliver the welcome address, please. Bhatnagar sir, over to you. Bhatnagar sir, are you there?
Shashank, thank you very much. And I will also welcome our professor, Shri Sachinal. And I welcome you all on this online tutorial on application guide for partial discharge and detection in GIS using UHF or acoustic methods, being organized by SIGRE under the aegis of SIGRE National Study Committee D1 on the material and emerging test techniques. Ladies and gentlemen, and all my participants, as you are aware that this is a unusual situation and new norms have been set. So this has affected our classroom activities, but nevertheless, we take the challenge and we have gone into webinar. And it is a great challenge. This is a great learning period for everybody. So accordingly, SIGRE India, with the guidance and support of SIGRE Study Committee, has planned this series of international tutorials to serve the professionals in particular and power sector as a whole. I am glad to share with you the excellent support and help extended to SIGRE India in achieving its objective or dissemination of knowledge effectively during current pandemic situation by SIGRE Study Committee D1 through our renowned Professor Dr. Way situation by SIGRE Study Committee D1 through Dr. Way Schneider, who is author of and co-author of more than 40 scientific papers. You are welcome, doctor, in this program. And he is also member of SIGRE OVVD and IEEE from way back. He is member from 2002 to 16, and he was convener of SIGRE AG D103 insulating gases and convener of other working groups in subcommittees D1 related to insulating material testing techniques and partial discharge at gas insulated system. I am very happy that Dr. Way Schindler has joined with us for today's session. I welcome you, Doctor. Welcome you. I also welcome Mr. Muni, Chairman SIGRE National Study Committee D1, and who is also General Manager with BHEL, which is a very known company in this country and world over. Is also who is an eminent professional on this subject, who is supporting and guiding the activities relating to National Study Committee on D1 as its chairman. I welcome you, Mr. Muni. I am also grateful to all the organizations supporting by way of active participating in these programs and taking advantage not only the individuals but the totality in the industry also. And once again, I welcome you all and hand over to Shri Muni for his address, please. Thank you very much. Thank you. Welcome, sir.
Thank you, Bhatnagar sir, for your welcome address. Unfortunately, Shri BP Muni shall not be able to deliver his address because of some technical issue. So we are still thankful to Bhatnagar sir and Muni sir for taking time from their busy schedule and joining us in this event. Now, moving further, before I invite our eminent speaker, Dr. Schindler, I would like to introduce him to all the participants. Dr. Schindler was born in Hanover, Germany in 1965. He received his diploma in electrical engineering in 1991 and PhD in high voltage engineering in 1996 at the University of Hanover, Germany. He joined Siemens switchgear factory Berlin in 1996 and was responsible for GIS product quality, technology, and condition monitoring. Since 2014, he is full-time professor at the Graz University of Technology in Austria and head of the Institute of High Voltage Engineering and System Performance. From 2002 to 2016, he was the convener of SIGRE AGD1 insulating gases and convener of other working groups at Steering Committee D1 related to insulating materials, test techniques, and partial discharges at gas insulated systems. From 2004 to 2012, he was the German representative on SIGRE Study Committee D1, Materials and Emerging Test Techniques. Since 2014, he is member of the Austrian National Committee of SIGRE and Austrian delegate for Study Committee B3 substations. In 2014, he received the SIGRE Tech Award from Steering Committee D1. He is also author and co-author of more than 140 scientific papers, member of SIGRE, OVE, VDE, and IEEE. Sir, I thank you for joining us in this event and agreeing to present your experience on the topic. Now, I would request you to kindly take over with your presentation, please.
Yeah, thank you very much for your welcome and the warm words to the beginning. It's my pleasure today to support the Indian SIGRE National Committee D1 and to give here my tutorial as follows. I will share now my slides. Wow, what happened? So I hope you can see the slides clearly and you can, everything is fine?
Yes, sir.
Okay, great. Thank you very much. So international tutorial today, online, of course, due to COVID pandemic. We have the 2nd December 2020. And I will talk about the application guide for partial discharge PD detection in GIS using UHF or the acoustic method. My name is Uwe Schichler and you can see my email address. So please feel free in case of any questions after the tutorial. You can send me an email and I will try to answer as soon as possible. Yeah, this slide shows my CV. It was already mentioned that I'm today a full professor at the Graz University of Technology in Graz, Austria. I was with Siemens HV switchgear factory, and I had also the chance in the past to visit the GIS factory in Aurangabad. This was always a very interesting meeting there with the Indian GIS experts. I convene some advisory groups and working groups. I received the technical award from Study Committee D1 in 2014, and currently I'm a member of SIGRE Joint Working Group D1B357, dealing with testing procedures for DC GIS, D163, dealing with partial discharge measurement under DC voltage, and the working group D166 is dealing with UHF partial discharge monitoring systems and is focusing on the properties and features, especially the generation of warning signals and alarm signals based on the PD measurement. Yeah, this is a short overview. On the right-hand side, you can see very nice pictures from GIS. We have here on top a 145 kV GIS double busbar system, 3-phase encapsulated. And on the right-hand side, this one and also this one are 420 kilovolt GIS. GIS is a well-proven technology used worldwide, and GIS show a very high reliability. But however, based on return of experience, some failures, some major failures, some breakdowns occurs. And this is one of the reasons that SIGRE experts deal with the partial discharge detection on GIS. And here on the left-hand side, you can see the front pages from the legendary SIGRE report in 1999. It was published in Electra and gave us the basis for the sensitivity verification for the UHF method and the acoustic method At that time, it was the first time that we really can make use of the UHF method, and on the basis of sensitivity verification with the partial discharge measurement according to the standard IEC 60270, and that was a very big step forward. The technical brochure here shown in the middle of the slide, 654, was prepared by the working group D125, and the technical brochure was published in April 2016. The reason to set up an application guide for the sensitivity verification was to collect the return of experience from the field based on the Electra paper, and this Electra paper with, let's say, 6 or 8 pages content gave some space for discussion, how to do it, how to interpret the results, etc. And the expert group here for TB654, they make it more clear, they define a few rules, and SIGRE gave, let's say, with this technical brochure 654, some strong recommendations when you apply the UHF partial discharge detection for GIS, and give a lot of clarification. And I'm really sure that in the near future we will find all these recommendations from SIGRE also in the IEC standards for GIS, for the GIS PD measurement. At first, I would like to give you and to share some information about the basics and the application of this partial discharge detection in GIS. And this slide, okay, it's a very dramatic slide, shows us some typical insulation defects in a GIS. So nowadays we are talking about 5 typical insulation defects. We talk about the moving particle, particles on insulation, protrusions, mainly on the high voltage conductor, that's really critical. We talk about floating electrode and void in insulators, so in epoxy parts, which can cause some damages. And of course, the GIS manufacturer, they are doing the manufacturing, the testing in the factory, and by quality assurance measures and proper routine testing, they will and they try and they do avoid all of these insulation defects. So the idea of the GIS manufacturers is, of course, to deliver a discharge-free, defect-free GIS modules or full erected base to the site for the installation. But anyhow, based on return of experience, some defects still occur, and they can cause some dramatic dielectric failures. So major failures can happen in service for GIS. Of course, this is a very rare event. Very often it's a single event, but based on defects which can be detected by proper partial discharge measurement. And that's the point that here SIGRE also listed the type of defects, and in combination with the description of these defects, of the critical defects. So here in this table we can see the critical lengths or diameters of a defect. We can see the apparent charge according to IEC 60270, so the well-known PC values, and also on the last column of the table we have the detectable length of the defect or diameter at nominal voltage, that means in service. Please remember that the routine test in the factory is done with an increased test voltage, and also the PD measurement is at least 20% above the service voltage. So that's the best chance to detect all the defects in the factory. And then the next chance is during the on-site testing which is very often done with AC voltage. Resonant circuit test systems are applied. Frequencies up to 150, up to 200 Hertz are used and combined with PD measurement. But during commissioning, the PD measurement must be sensitive enough that we can detect all the critical defects in the GIS. And as you know, if you have a big GIS, maybe with some 10, 15 or more than 20 bays, it's a very time-consuming procedure to do a proper high voltage test, including a sensitive partial discharge measurement. And to have a look to the details, see Gray mentioned that for moving particles, the free moving particles, a length of 3 to 5 millimeter or longer is critical. Such particles will give us in a laboratory some apparent charges of 2 to 10 picocoulomb. For protrusions on the high voltage conductor, they are still, or they are all critical, even if the length is only 1 millimeter. This is not really long, but this will reduce the lightning impulse withstand level to the half of the value if there is a protrusion on the high voltage conductor with a length of 1 millimeter. This defect is showing an apparent charge of 1 to 2 PC, so really hard to detect also in the factory testing. Protrusions on enclosure, they are critical when they have a length of 4 to 6 millimeters or longer, and at that position they show to us an apparent charge of 2 PC by the measurement according 60 to 170. Particles on insulation, critical length 1 to 2 millimeter or longer, and this will give us about 0.5 picocoulombs only, so this is really hard to detect. The voids are critical in epoxy parts when they have a diameter of 3 millimeter or more, and these voids will give us some apparent charge of 1 to 2 PC. And now we have to have a look here to the statement. This is written in the IEC standard 62271-203, so the standard for the GIS. They accept a level of 5 PC according to the IEC measurement 60-170. Of course, all manufacturers, they have improved their quality, they have improved their partial discharge measurement in the past. Today, we have a noise level for the PD measurement in the factories of about 1 to 2 picocoulomb. So when you share this information with the table, most of the critical defects can be detected in the factory. The IEC 60-170 method, which is defined for lumped circuit elements, cannot be applied on site because we have for the IEC 60-170 PD measurement, we have to apply a coupling capacitor, which is not available, or let's say not possible to build up for most of the GIS, especially not for the 400 and 500 kilovolt GIS, and also not for the 1100 or 1200 kilovolt GIS, which are in use in China and also in the testing stations here at India. So we cannot apply the 60-170 method on site for the GIS. Also, a big GIS has nothing to do with a lumped circuit. So the experts in the past, they invented some PD measurement techniques, some non-standard PD measurement techniques. The first one here highlighted in red is the ultra-high frequency method. It's a PD measurement in the frequency range from about 200, 250 megahertz up to 1.5 or up to 2 gigahertz. We will discuss this here in detail. There's also another method called the acoustic method. Here we have an acoustic sensor, and we are hearing to the sound from partial discharges inside the GIS. It is also in application. And then we have also some more PD measurement methods, the optical one, the chemical one. These are, let's say, methods which are used in the laboratory, which were investigated in the past and also nowadays. But the performance of these measurement methods is not as high as here for the ultra high frequency. You see here the equivalent circuit for the ISC 6270 PD measurement, and here on the bottom you can see a typical PRPD. This is now standard, nowadays standard, or let's say standard since more than 15-20 years for the visualization of partial discharge impulses. And by these 3D pattern, so we have the magnitude, we have the phase angle in relation to the 50 hertz power supply voltage, and the color gives us a number of PD pulses. So we end up with some nice pattern. And here on this pattern, you can see some PD from a void, and human experts with some training can identify the type of defect here by checking the PRPD charts, and also today's automatic expert systems, let's say artificial intelligence algorithms, can identify the type of defect. The pattern on the left-hand side, that's a typical diagram from the former PD measurement using the UHF method. You see the time of 50 cycles, the phase angle again, and the magnitude of the pulses. So some people are trained on the PRPDs, other people are trained on the single cycle diagrams. At the end of the day, the human expert or the artificial intelligence algorithms should tell us what is the type of defect causing these patterns. Some basics for the UHF PD detection. Here in this slide, we will start on the top left corner. We have a tube from a GIS. We have a discharge in this position, and we have a coupler or sensor. It's a small antenna inside the chamber, which is connected to an oscilloscope. And when we increase the voltage on this chamber, this defect, it seems to be a needle, a protrusion on the chamber. We will have this type of impulse, which can be measured in laboratory with some artificial defects, etc. The main point of this impulse is that this impulse is in the picosecond range. So we have a very short PD impulse with a steep time of some hundreds of picoseconds. And this discharge sent now some electromagnetic waves which will travel inside this chamber, and after a certain time the electromagnetic waves are coming to the coupler here, and we can see the time signal on the oscilloscope. And this is shown here on the right-hand top diagram. We have a PD pulse visible on the oscilloscope, but the main point now is that here the origin was a very short impulse in the picosecond range. Now we have a signal which is very long, which is ringing here around for more than 50 nanoseconds. This is something which we have to notice for the UHF PD measurement. The very short impulse is changed by the GIS structure, by this waveguide, to a signal which is in time, let's say, very long, and we have some resonance frequencies shown here as maximum and minima, and we have to investigate this time signal for PD pulse interpretation. The second thing is, which was also discovered in the late 80s in Glasgow, that when we have the same discharge here and we connect a spectrum analyzer for measurement in frequency domain to our coupler, we can see such a frequency spectrum. This spectrum is started at 0 Hertz, is going up to 1.5 gigahertz. And this impulse, this very short impulse, and it's only one single impulse, is giving us such an amplitude spectra in frequency domain. We can see that the impulse transfer from the source to the coupler is working fine in some frequency areas, and here, for example, above 1100 megahertz, there is a big attenuation, there is no signal detectable. So when we talk about UHF PD detection, we have to take into our mind always these very long impulses in time domain, and we have to think about the frequency spectra in the frequency domain. But anyhow, after some first developments of equipment for measuring UHF partial discharges, nowadays there are more than 1,000 partial discharge monitoring systems are in operation worldwide. They consist at least of the couplers, which are mounted in the GIS. Then we have some, here it is called optical converter units. That means that we have a converter which pick up the high frequency signals and converts them to low frequency signals, and the signal transfer here is then done normally with fiber optics to be protected against EMC. And then all these OCUs, which are distributed all over the GIS, the signals are coming to the PDM equipment cabinet where the data are stored. It's really a 24/7 measurement. So today's systems can pick up each PD pulse from the GIS, store them, and can make an evaluation for that. And here on the right-hand side, we can see some couplers mounted in the GIS. So this is example A. This is example B. Later on, we will see some more examples. And such a cabinet here with industrial type PC, with some intelligence, with a UPS, with a connection to the SCADA system, and also with a man-machine interface for on-site working is shown here. And at the end of the day, we have these typical PD displays, which show us if there is PD available, yes or no. And by proper interpretation of these diagrams, we see the typical defects in the diagrams. So such systems are available, they are in use, and SIGRE is just now on its way to make some definitions for the improvements of the PDM systems, especially for the back end, so where we have the PD signals and where we have to generate some warning and alarm signals. Not each PD impulse is harmful. Sometimes a warning is okay. It must not be an alarm, but all the different manufacturers and users, they are using different criteria for the generating of warnings and alarm signals, which are sent to the SCADA system. And to make the world better and to avoid false alarms, SIGRE is looking for some common rules and settings for the generation of these signals. Let's change over to the acoustic PD detection. Here the basics for the acoustic PD detection are shown. On the top we see two typical defects, the particle and the protrusion. This will give us a discharge. So, and here, and that's the point, outside of the GIS, we have an acoustic sensor which must be placed on the enclosure from outside. And if there is a particle moving, then it is always hammering here on the enclosure from the inner side. And the small ping signal is then sent in the enclosure by traveling waves, acoustic traveling waves, to the acoustic sensor and can be picked up at that point. The same if you have a discharge in the gas, it's like a small gas explosion. And we will have some pressure waves which are traveling in this direction to the enclosure, and inside the metallic enclosure, then we have also a proper waveguide and the signal can be picked up by the acoustic sensor. So it's a very easy test, is like at the medical doctor when he is checking your heartbeat. So, and from this acoustic sensor, we can take also the signal here in time domain. You see the AC voltage waveform, and here we have 1, 2, 3 acoustic events. You see we have clear signals which can be picked up, and there are also some equipment, PD instruments for the acoustic PD detection available on the market. Here we can see the sensors more in detail, and here inside this green circle you can see one acoustic sensor which is mounted on that particular enclosure of the GIS. And for the acoustic measurement, we have some attenuation. In the metallic enclosure, we have an attenuation given by the flanges. We have a lot of attenuation for signals from voids in epoxy. So the PD detection by the acoustic method is not so powerful like the UHF measurement. And the other thing, it's very time consuming. Here you can see a cross-section of an old GIS, generation number 2, I think, but it's a typical overview and cross-section, and all these green dots which are shown here and also here in the cross-section, these are the locations, the necessary locations for acoustic sensors. So at the end of the day, you have to measure the acoustic signal at each compartment. And this is of course difficult if you're doing this during the on-site testing, and it is time consuming if you have a limited number of sensors available. But anyhow, there are a good chance to measure particles. The acoustic method is very, very sensitive for particles. You can have the time signals here. This is an example from a protrusion on a high voltage conductor for different voltages. Left-hand side 60 kilovolt, right-hand side 80 kilovolt. You can see clear signals in the time domain measurement with the oscilloscope, and on the PD instruments you can also see these pictures in a certain way, and by evaluating you can make identification of the defect. But to summarize the application of the acoustic method, we can mention that it is very, very sensitive for particles. Voids, for example, cannot be detected due to the high attenuation of the epoxy. The testing is very time consuming. some acoustic PD instruments are available, and sometimes they are used in the laboratory and during on-site measurements, but acoustic partial discharge monitoring systems are, according to my knowledge, are not available, and the reason is quite clear. It's not reliable. You need too many sensors. You have a limited detection sensitivity compared with the UHF method. So the acoustic PD measurement method is available, can be used, but it's not in application for continuous partial discharge monitoring. Let's come now to the very important sensitivity verification procedure. In the past, everybody was keen on picocoulomb values of partial discharges, and also the standard is telling us 5 PC, that's the acceptance level. What does it mean? First, we have to remember that this value is an apparent charge, which is detectable at the connection points of a specimen. It's not the real charge at the point of origin of the partial discharge. So that's a big problem. And the other problem, what is the meaning of 4.9 picocoulomb? Is it okay? And 5.1, we failed. So we have always in the SIGRE groups a big discussion about the definition with picocoulombs for the partial discharge characterization. But anyhow, it is given in the standard, and this is a very good platform, a common agreement between manufacturer and user, that we have a kind of acceptance criteria. And at the end of the day, this needs to be mentioned, the feedback is not bad based on this 5 PC value. The problem is that with the UHF method, and also not with the acoustic method, we cannot measure picocoulombs. That's not possible. And when the UHF method and the acoustic method was introduced and getting more and more in application for the on-site commissioning, and the first partial discharge monitorings came up at that time, as there was a big confusion. What is detected? What is measured? Are we too sensitive, or is the sensitivity not okay? So how to handle, how to do. And the SIGRE Task Force 15-33.03.05, they published in 1999 a paper in Electra with the title Partial Discharge Detection System for GIS, Sensitivity Verification for the UHF method and the acoustic method. And that was the starting point of a common agreement between the manufacturer and the users to apply the UHF method on site. And the starting point is mentioned here again. The UHF method cannot be calibrated in picocoulomb. Anyhow, we need a procedure for sensitivity verification. And this procedure is a two-step procedure, and it was introduced by the SIGRE paper in 1999, so more than 20 years ago. And these two-step procedures consist of step 1 in laboratory and of step 2 on site. But let's focus first on the step 1, which need to be done in the laboratory of the GIS OEM. At that laboratory, the manufacturer has to set up a certain kind of test setup, where we have couplers, coupler C1, coupler C2. At coupler C2, we have the UHF measuring device connected, could be a spectrum analyzer, could be an oscilloscope, or could be also a modern partial discharge monitoring system. And here at that position, we will place a defect. And in the past, this was always a moving particle. And then we increase the voltage for this test setup, and we increase the voltage as long as this moving particle is showing us a PC value of 5 PC. Because that is stated in the standard, 5 PC is the acceptance level, so the Siegel group focused also on this 5 PC level. So we have now here a moving particle under voltage showing us a PC value of 5 PC by IC 60270 measurement. And in that case, when we have this 5 PC value, we make a reading of this signal A, whatever it is, millivolt, dBm, percentage, frequency, amplitude, doesn't matter. We make a notice here, a note of the signal A. So now we reduce the voltage back to 0, and we connect an pulse generator to the coupler C1. And C1 is at the position of the defect. And with this pulse generator and step impulse from 0 to 1 or whatever voltage, we introduce a UHF signal here into the chamber. So the voltage step via coupler C1 is generating UHF signals, which will travel to coupler C2, and we will have again a reading of the signal B. And now that's very important. We increase the voltage at this pulse generator as long as signal B is matching with signal A. That's very important for the step 1 in the laboratory. And at the end of the day, we have a correlation between the 5 picocoulomb from our defect with the magnitude of the signal from the pulse generator. And that's all for step 1. So the laboratory test has to be performed to determine the magnitude of the artificial low voltage pulse related to the real PD signal, and that's a prerequisite for step 2. And all major GIS manufacturers which are using the UHF measurement, they already did these step 1 laboratory test, and they should present to you a kind of report or certificate where they show the test setup, where they define the defect and the pulse generator with its magnitude, which is equivalent to the 5 PC value. And one result from the return of experience from all over the world is that for a specific GIS, a specific design of the couplers, for a defined pulse generator, and for a specific UHF measurement device, the end result is a voltage step of 20 volt is equivalent to an apparent charge of 5 PC caused by moving particles. This is the one and only outcome of the step 1 in laboratory. And the measurements itself, once again, here for the UHF measurement, can be done in time or frequency domain. We will see some examples later in this tutorial. So this was step 1. And step 2, on-site, is very simple. We will take the same pulse generator, we will inject the voltage level here to this coupler, and then we have a look to the adjacent coupler, which is here on the bus bar section. And if we inject the equivalent voltage level to 5 PC, which was on the example before 20 volt, if we see the 20 volt signal here at the adjacent coupler, then we are sure that the section, the full section of the GIS between the two couplers is sensitive, monitored with a level of 5 PC. So that's quite clear. We inject the signal, we measure it on the adjacent coupler. If we can measure it, then everything is fine. If we are not able to detect the injected signal, this is shown here on on the bottom, then the number and location of couplers should be improved, or a measuring device with better detection sensitivity should be used. So if we fail with this sensitivity on the first check, then we have some possibilities to improve the situation on site. So this is the full idea behind the sensitivity verification check invented by Segre in 1999. Very simple, and from that day onwards, everybody was using this worldwide. There are a lot of publications available which show the benefit and the application of this procedure in detail, and a lot of GIS were tested according to that procedure, and a lot of defects were identified, were removed from the GIS. So it was really a step forward on the quality of the GIS, and the reliability of GIS was improved by this procedure. The same can be done for the acoustic method. This is here for completeness of the description. When we do the same for the acoustic method, we have in the laboratory the step 1. We have a GIS module, a GIS compartment. We have a sensor here. We have an acoustic sensor on that position. We have a defect here inside the GIS. And the step 1, again, compared to the UHF method step 1, we will increase the voltage until we have a signal of 5 PC. We have a reading at the acoustic measurement device. Then we will use the step generator. We will activate the first coupler, the first acoustic sensor here at that position of the PD source. We will pick up the signal, and then we have the correlation between the voltage, step response here, step voltage, and the reading on the device. And the same need to be done on site. So if we can measure the stimulated acoustic signal at the second acoustic sensor, the sensitivity verification has been successful for the GIS section between these sensors. Yeah, after these basic informations, I would like to go more into detail for the technical brochure 654, which has a title, UHF Partial Discharge Detection System for GIS Application Guide for Sensitivity Verification. And I already told to you in the beginning, after 1999, the procedure was used and everybody was thinking a little bit different about the description, and there was some room for improvement. And this was done by the members of the working group D125. Their task was to collect the experience from the field and to make an application guide to improve these first definitions from 1999. And in 2016, this brochure was published, and a lot of, let's say, improved definitions are part of this technical brochure. The brochure itself is, of course, free of charge, available at the eSegre homepage. So if you have not this technical brochure with you, please register for the download, and then you can get it for free. That's the big advantage of Segre, that all these documents are free from day 1 onwards for Segre members, and after 3 years it is also free for the public, but the only thing is that you have to register, but that should not be a big problem. So let's talk about this technical brochure 654 in detail. And first I would like to show you the members of this working group. You can see the names of the members. The convener, that was me. My secretary was Wojciech Kultonowicz from Omicron. And then we had with us some people from General Electric, We had some people from ABB, from TEPCO in Japan, from EDF in France, from Australia. We had some member also from Switzerland, from a testing institution. The manufacturers were with us, so Carsten Jure from Siemens in Germany, Uwe Richard from ABB Switzerland, Klaus Neumann was from a utility in Germany, and the company DMS, nowadays Qualitrol, John Pearson was also with us for this working group. So we had members from utilities, from the GIS OEMs, from universities, and from PD instrument OEMs. And the structure of the technical brochure 654 is listed here. In this brochure, you will find a detailed introduction, then the fundamental UHF PD signal propagation characteristics are described. This is important that you understand the traveling of the electromagnetic waves inside the GIS. In the technical brochure, we have a proper description of the sensors. Sensors can be built in, can be also external sensors. We had the proper description of the type of PD defects, and we make it more clear in this technical brochure 654 that we should not longer focus only to the moving particles. We also should focus to the protrusions on the high voltage conductor. Then some guidelines and recommendations and descriptions were set up to make a better definition for the procedure of the sensitivity verification step 1 in laboratory, also a better description for the sensitivity verification step 2 for the on-site testing, and it is summarized then with guidelines and recommendations, and it finished with the conclusion. So this is, let's say, the standard introduction. I will rush through this information here very quickly. We have the information that GIS have been in operation for more than 50 years nowadays. They show very low failure rates. However, return of experience show that some of the in-service failures are related to defects. Many of these defects can be detected by PD diagnostics. The UHF method is nowadays worldwide in use by the GIS manufacturers in the factory during commissioning and by the utilities for monitoring and service. And this is really based on the positive return of experience from the field. Here a short description about the 1999 Siegel report. This was the first time where we introduced the sensitivity verification, and the proposed procedure ensures that defects causing an apparent charge of 5 pC or greater can be detected by the UHF method. Let's say the problem was that this Siegel report described the two-step procedure in a very general way. There were some discussions around all the years, and it was obvious that a more detailed description of the various sensitivity verification is necessary to avoid technical misinterpretations. So working group D125 collects all the available experience of the sensitivity verification for GIS, and we made this application guide for an improvement of the UHF method for PD detection. The fundamental UHF signal propagation characteristics, again, we have some information about the electromagnetic waves, which are up and also over 2 gigahertz. They are running around in the GIS. We have a coaxial structure of a GIS. The signal propagates by the speed of light, in different modes, TEM, TE, and TM. TE means transversal electric, transversal magnetic. And we have also some discontinuities in the arrangement of GIS, where we have changing diameters on the high voltage conductor. We have conductors, we have shieldings, we have the disconnector electrodes, we have the big compartment of the interrupter units at the circuit breaker. And this is all a change of the impedance of the GIS, and every time when we have such a discontinuity, we have a reflection and some attenuation of the PD signal itself. That's the reason why we always lost some magnitude when the signal propagates along the GIS. So, and to summarize, the propagating signals, the PD signals, undergo both loss in amplitude and dispersion. Great, so sensors, that's very important, and there are so many different sensor designs are available, and that's sometimes confusing, and therefore we have here some examples for these sensors which might be built in the GIS from day one onwards on defined locations. We can also have some external sensors here at the barriers or at the inspection windows, which can also be retrofitted to a GIS. So to mention the main important information, so we have the internal sensors. They must be fitted to the GIS during manufacturing. They also can be retrofitted during maintenance, but this is costly. These internal sensors often take the form of a metal disc insulated from the GIS enclosure by a dielectric material. At the end of the day, this sensor acts like an antenna. So, and for the external sensors, they are also called window sensors and barrier sensors. Yeah, they are fitted to an open point, to an aperture in the chamber wall, where we can measure the electromagnetic waves which try to go out of the GIS chamber. So we have internal sensors and external sensors. Then very often a discussion is started about the sensor performance and about the frequency response of these sensors. And the SIGRE group had a very clear opinion. At the end of the day, you have to fulfill the sensitivity verification step 2 on site. So you need a sensor and you need a PD measurement instrument. And of course, you can use, let's say, a poor sensor and a very good amplifier at the PD measurement instrument, and you can fulfill the sensitivity verification step 2 on site. So everything is fine. But it can be also vice versa. You maybe use a very good sensor and let's say UHF measurement system with limited amplification, but if you pass the sensitivity verification step 2, everything is okay. So you can improve and you can focus on the sensor performance, but it's better to look always to the complete measurement chain. That means sensor plus the measurement instrument, including all the amplifiers and so on. So that's the reason why I highlight this sentence in red. Sensor performance can be checked when the sensor is installed in the switchgear by the use of the SIGRE sensitivity verification procedure. If you want to focus on the sensor itself, this is very often done by young researchers. Yeah, they using some standalone specific calibration cells or some conical injection and termination elements on the GIS components. This is a GTEM cell, but please remember you are only dealing with a sensor, not with the full system. But of course, it's nice to know the performance of the sensor and also the frequency response of the sensor itself. Some information about the PD defects again. We already know that slide. And when we go more in detail for the step 1, for the laboratory test, we have to really go more into detail. And the signals which are measured with the UHF method depend on a lot of factors which need a definition. So we have clearly to define which type of defect we are using in the laboratory test. Then we have to talk about in detail about the location of the defect within the GIS compartment. We need to mention the propagation effects, reflection, interferences, attenuation. The position of the sensor relative to the defect has to be reported, and the signal transmission path between these two couplers C1 and C2. The characteristic of the sensor, if it's available, its own transfer function, and we have to check the characteristic of the complete chain of the measurement system from sensors to data acquisition and display. And these need to be done in a very precise way, and this need to be all documented in a report. And once again, the look to this sketch here for the laboratory test. We discussed this already, and you will agree that it is not clear which type of test setup should be used for that. Should be this tube in the middle here, should it be 1 meter long or can it be 10 meter long? What's about the terminations on the left and on the right hand side? Here it is shown like an open end, but this cannot be true for a real GIS. This needs to be gas filled, and so we need some covers at the ends. So how to handle this? And we made some investigations, and we agree on 2 different high voltage test sets for the step 1 in the laboratory. One possibility, especially for single phase encapsulated GIS of 420 kV or higher, we said, okay, 2 adjacent couplers at 2 adjacent compartments, that's okay for the sensitivity verification step 1. We have the sensor C1 in this position, we have an insulator in between, we have a sensor C2 on that point. This is under high voltage, and here on the opposite side of the sensor C1, we have the defect location. So such a setup is agreed by TB654, and on the other hand, so especially for 145 kV GIS, which are 3-phase encapsulated, we accept also that the test can be done on a full bay. So we have one sensor here at the bus bar, and we have a second sensor C2 at the cable termination module, and the sensitivity verification should be done with the defect very close to sensor C1, and we can do with such a setup the sensitivity verification step 1. These 2 setups, these 2 kind of setups are agreed for the laboratory test setup. And this was a big improvement, that we make clear what is the expectation by C. Gray for a proper sensitivity verification check. So we have to take into account that there are different measurement systems are on the market. We have some narrowband systems which are measuring in a very small frequency range of some tens of megahertz. And on the opposite, we have broadband systems which measure here from, let's say, 300 MHz up to 1 GHz. This fits more for the partial discharge monitoring systems. And the UHF measuring device, which is used, what is the technique behind? Also, that need to be discussed, let's say, in front of the step 1 test. But then if it is fixed, then it has to be reported in a correct way, that everybody knows which instrument was used and what were the settings of that instrument. Otherwise, you cannot compare the results from step 2 with step 1 when you do the on-site measurements. Some words for the pulse generator. These pulse generators, these small handheld generators, need also to show a proper function and performance. So the rise time of the artificial pulse need to be the correct one. We have here the rise time of the artificial pulses must not exceed 0.5 nanoseconds to stimulate the high frequency signals in the GIS. The magnitude of the pulse voltage need to be checked carefully. The time between consecutive pulses should be about 50 Hertz. So 1 artificial impulse per second, that's fine for use it for the UHF sensitivity verification. Very important is the same type of pulse generator must be used for the on-site test. Don't change the equipment, don't change the pulse generator type between step 1 and step 2. That's also very important. To match the real PD defect and the artificial pulse magnitude, there are 2 possibilities. One possibility is to do this in the frequency domain, as shown here in this diagram. We have in green the frequency spectrum from a 5 PC defect, and if we inject with the pulse generator a 2-volt signal, we have the blue curve. And now we can change the voltage level also to 1 volt, to 5 volt, to 10 volt. And we have to look for the best match of the 2 amplitude spectra here in the frequency domain. This can be done by visual comparison, but this is always influenced by the expert who is doing this visual comparison. So it is much better, and these techniques are available to use some statistical tools. So please compare and document the average amplitude, the maximum measured power, and the average power of the frequency spectrum in the applied frequency band. Please remember narrowband and broadband systems. So here we have to stay to our technology. So if we use a narrowband system, then we have to also this comparison with the statistical tools for exactly that frequency band, which is used later on for PD detection. So, and when you do such experiments in the laboratory, you end up with some values. For example, you use the moving particle as a defect, and you get these values for MP, AP, and AA, minus 25.7, minus 50.9, 53.4, and then you compare these values with the output values of the 2 voltages, 10 volt and 20 volt, and you can see this is indicated by the red arrow. In this case, the 10 volt signal fits well to the moving particle signal. So the outcome of such a test will be here in this case, 10 volt is equivalent to 5 PC of a moving particle. And that's it. So the second possibility is to determine the artificial pulse magnitude in the time domain. using PRPD pattern. So when there is a jumping metallic particle, you are getting the typical pattern here, which is shown on the left-hand diagram. So this UHF signal here is equivalent to the 5 PC value. And if you take the pulse generator, you inject 2 volt, 5 volt, 10, 20, and 50 volt, you can compare the voltage level of the impulse generator with the pattern, and here indicated by the red line, we have the result that 20 volt is equivalent to 5 PC of that moving particle. And this is a result, let's say, from a different GIS, different manufacturer. So please don't compare these measurement in frequency domain and time domain. At the end of the day, both measurement techniques should give you the same voltage level for the artificial voltage magnitude. So here, as an example, an artificial pulse magnitude of 20 volt is equivalent to 5 PC for this specific moving particle. So we have two ways to determine the magnitude of the pulse, of the artificial pulse. Another point was identified during that investigations, and such a working group normally work for, let's say, 3-4 years to collect all the information and to prepare the final report. Some special laboratory tests, some experiments were agreed and done, and it was obvious that we found in general different voltage levels for the artificial pulse magnitude when we compare protrusions on the high voltage conductor and moving particles. So for another example, it was here shown that for the moving particle with 5 picocoulomb, we have a 10 volt signal, which is equivalent. And if we change the type of defect to protrusion on high voltage character, we found, oh, the artificial pulse magnitude is only 2 volt. So, and that is also a new outcome from that technical brochure 654. For different type of defects, we have different voltage levels for the artificial pulse magnitude. So, and now we have a kind of dilemma. What should we do for the step 2? Should be the arrangement of the couplers in the GIS for the more critical defect, the protrusion, or will we go ahead with the equivalent to the moving particle, which is 10 volt? So this will give us a different number of couplers on site and a different layout of couplers on site, and this need also be checked and defined during the specification of a partial discharge monitoring system for GIS. This need to be mentioned in the tender, which type of defect should be applied for the sensitivity verification step 1. Should you be very sensitive, then you would go for the protrusion, because if you are able to have the sensitivity check passed on a 2 volt level, then you of course fulfill also the 10 volt requirement for moving particles. If you only focus for the moving particle and you say, okay, the 5 PC equivalent should be from moving particles, then you will have some locations of the coupler, some sections of the GIS where you cannot measure the 5 PC protrusions. So this was one outcome, and this need to be defined in the specification of the GIS of the PDM system, that the manufacturer can do the correct placement for the location of the UHF couplers, the sensors at the GIS. So different type of defects gives us different artificial pulse magnitudes when they are indicating 5 PC apparent charge. The Step number 2, general aspects. Step number 2 here on the bottom, on-site test. Now here with the second step of the SIGRE sensitivity verification, we use the same type of GIS as used in the laboratory test. We use the same sensors, the same UFF measurement or monitoring system. So with the second step, in that case, we check does the on-site installation has sufficient sensitivity to detect the signals. And during that time, we also check the functioning of the sensors and the measurement chain, because you have to connect the sensors with some cables to the converter units, and from the converter units you have to go to the cabinet where all the signals are collected. So second step of the SIGRE sensitivity verification, main job is to check if the installed system has sufficient sensitivity to detect the required PD signals. Second bullet point, so it is understood that the same type of sensors, the same pulse generator must be used. Step 2 should be carried out with the same measuring system which was used at step 1, or with a system with similar or better detection sensitivity. That's quite clear. In general, the on-site sensitivity verification is fulfilled if the injected artificial pulse can be measured at the adjacent sensors. We discussed this already. And we need a certain number of sensors due to the attenuation of the PD signals within the GIS during their traveling of the electromagnetic waves. So the number of sensors required to be installed in the GIS depends on the PD defect and the required detection sensitivity. This was mentioned here before. Based on the type of defect which you want to detect, the number of sensors required to be installed is dependent on that information. So the sensor location itself, to make it more clear, we have, let's say, a drawing of one GIS bay. We have the double bus bar here. We have a circuit breaker. Then we have the outgoing feeder to a directly connected transformer. And based to the 1999 SIGRE report, we have to build in 3 sets of couplers, one here at the bus bar, one in between, and one at the bushing here of the connection point of the interface between GIS and transformer. And the step 2 is working in that direction, that we have to take the impulse generator, that we have to inject, for example, here at the coupler number 2, the signal, and then we must be able to detect at the adjacent couplers 1 and 3 these artificial signals. If we detect it, then everything is fine. If not, then we need maybe another coupler here at that point, or we have to have an instrument with higher amplification of the signal. But it is quite clear, you have to take the impulse generator, inject at number 1, then you must be able to pick up the signal at coupler 2, then you inject at coupler 2, you must be able to pick up at coupler 1 and coupler 3, and on the last step you have to inject the signal at number 3, and you must be able to pick it up at coupler number 2. That's a full sensitivity verification check on site, and all the results need to be documented. So in this period of commissioning, we have to do also this kind of measurements for a quality check and for a sensitivity check for the partial discharge measurement system for the UHF PD detection method. Right. So, and when we go more in detail, we have here now two bays of that GIS. We have one bay which is connected to a high voltage cable, and we know already this bay which is connected to a transformer. If we have a look to the single line diagram, we have 5 locations of PD couplers, PD sensors, A, B here in the bus bar, C in the bus bar, D and E on the outgoing feeder to the transformer. And the sensitivity verification check step 2 need to be done for all these couplers, for all the 5 couplers. So we have to inject from A to B, from B to A, from B to C, from C to B, and so on. That's time consuming, okay. This needs 1 or 2 days on site, but this is the prerequisite for a proper UHF PD detection during the commissioning test or during service later on. This pattern here, or this picture on the bottom, shows us a very simplified attenuation profile of the UHF signals. That means if you inject a signal equivalent to 5 PC at coupler B, then the signal attenuation will give us a smaller value at the location of coupler A. The same when we inject at coupler B, we have the attenuation in direction to coupler C, and we have a certain reduced level at coupler C. At the end of the day, we have an overlap, we call it attenuation profile for this GIS, and you can be sure that each GIS section is monitored with a sensitivity of 5 PC, or if you go in detail and you think about a defect in the middle between 2 couplers, you can say you have an improved or a better sensitivity, a better detection sensitivity than this 5 PC based on the location of the couplers. So from a general point of view, we have a distance between 2 sensors, typical in the range of a few meters to approximately 20 meters. This is dependent on the GIS design, on the voltage level, etc. But it is also true that this distance between 2 sensors can be extended up to more than 100 meters in the case of GIL or GIB. That's based on the perfect coaxial structure of GIL or GIB. Yeah, the TB654 also discussed alternative method for the location of the sensors. We can think about to cancel these sensors at the positions A, C, and E. Yes, you are sensitive for the detection of the 5 PC defects, but the step 2 will be much more difficult. Anyhow, this can be discussed, and this can give benefit in direction to the reduction of the number of couplers, which has also an input of the, let's say, design of the PDM system. So if you want to reduce the number of super or monitored PD couplers, you can go with one of these proposals for the coupler number reduction. Another point was discovered during that working group time, that the position of the switching devices is also influencing the result of the sensitivity verification step 2 dramatically. This was not well known in the beginning, but here with TB654, this is now clear and available for the public, and you have to decide for the step 2 the position of the switching devices. The example here is coming from a 3-phase enclosed 145 kV GIS. We have a PD coupler here at the bus bar where we inject the artificial signal. The measurement is done on the second coupler here at the cable termination housing, and we have some switches in between, Q1, Q2, Q0, the circuit breaker, and also the disconnector Q9 in direction to the cable. And here the table on the left-hand side show us the detection level when we inject the same signal, always the same signal here for injection at the busbar sensor. So if we have a switching device position of close, open, close, close for the switches Q1, Q2, Q0, Q9, we end up with 70%. 70% of signal received by the sensor here at the cable termination. If we have a switching position characteristic like Q1 is open, Q2 is closed, Q0 is closed, Q9 is closed, then we end up with a 100% value. And if we have a situation that all switches are in open position, we end up with only 58%. So you can manipulate the result of the sensitivity verification step 2 with the switching position of the different devices. So to do a proper step 2, the switching positions need to be defined, and this has to be taken into account for the on-site sensitivity verification, and it is recommended to apply the most common switching situation of your GIS for this procedure. That can be checked also in the frequency domain, showing the same effect. And here it is the summary of that part. It is recommended that on-site sensitivity verification should be carried out for the most frequently used configuration in service. Yeah, so there is no need to check it for all combinations. Make a definition about the most frequently used configuration, and therefore the step 2 test should be performed. We are coming more or less to the end. The TB gives also a description about the sensors. Main output, same type of sensors must be used during step 1 and step 2. That's also valid for the pulse generator and the measuring equipment. Don't do it that you have a frequency domain measurement in step 1, and in step 2 you apply a time domain measurement with PRPDs. That's not okay, that's not correct. This will give us some misunderstandings and some false results. This test needs to be done for each GIS section. That's quite clear. The test can be done during commissioning as well as during regular operation of GIS. And to pass this on-site sensitivity verification, the measured UHF signal should be clearly above the noise level if you work with PRPDs, or it can be considered as sufficient when some resonance frequencies clearly appear above the background noise spectrum if you are working with a spectrum analyzer. So a lot of details need to be considered, and the technical brochure ends with some clear guidelines and recommendations, which I would like to show to you. This is a kind of summary, a very comprehensive summary of the chapters in this technical brochure. Here we have for the sensitivity verification step 1, a description of the aim, the definitions for the test setup, the PD defect and detection sensitivity, sensors, PD measuring device, pulse generator, determination of the artificial pulse magnitude, and of course the result of this step 1 should be documented properly in a report. And we have also some guidelines and recommendations for the step 2. This is the aim of the step 2. the principle, the arrangement of sensors, the position of the switching devices, the test equipment, and that's very important, the criteria to pass the test. And all these findings from testing should also be documented in a report. And as here for my final slide, a short conclusion. We have from 1999 the two-step procedure for the sensitivity verification of the UHF system to make it applicable for the GIS during commissioning and monitoring and service. The technical brochure 654 collects the available experience and prepared an application guide, and these established guidelines and recommendations will help manufacturers and users in the effective application of the UHF method for PD detection on GIS. Ladies and gentlemen, thank you very much for participating and for your kindness to listen to me. That was the last slide here, and it would be my pleasure now to discuss with you and to answer your questions. Thank you very much.
Thank you so much, sir. To all the participants, I'll request you, the panel is open for discussion. You have the opportunity to interact with sir. Dr. Sister, there are some questions in the chat box.
Yes, I will check that here when it started. Yeah, just wait. So the first question was whether manufacturer of PDM system downgrades the UHF signal for further analysis or they analyze directly UHF signal. Please clarify. Now, each PDM manufacturer downgrades the UHF signal by a proper signal treatment, and they handle the low frequency signal, which gives a lot of benefit for the hardware and software of the systems. And the analysis of these, you call it downgrade, I will say adapted signals are the basis for a good analysis of the original PD pulses. If the OEM of PDM system downgrades the UHF into HF and then perform further analysis, will it affect result of PD? You need to check that. When you talk to PDM manufacturers, everybody is telling you that it is perfect, but at the end of the day, you should have a look to their test results from laboratory test step 1, step 2, and from some on-site measurement, that they are really able to detect the PD signals. And it is very important that also their artificial intelligence algorithms, the PD expert systems for PD identification, works very well. So also the new working group, Secret D166, will give strong recommendation for the factory acceptance test of PDM systems, because we noticed that there were also some, let's say, misinterpretations or failures in that part. Next question. How would we distinguish between PD occurrence and external noise, external corona discharge and actual one? All the PDMs, they have some special, let's say, functions to cancel the noise signals and to focus only on the real PD signals. This can be done by software filters, by hardware filters. So corona from corona in air, they have a bandwidth with about 300 or 400 megahertz. And if you apply a high-pass filter to the input of your PDM system, which start with a cutoff frequency of 500 megahertz, then you can cancel the corona discharges. Another possibility is to have a coincidence filter for single-phase encapsulated GIS that's working well if you have at least on 2 phases of the GIS at the same time interval of 1 microsecond signal, then it cannot come from the GIS, then it must be a signal from outside, and they were cancelled from the further data handling. So these algorithms, these functions are available, but of course it needs some time and some experts to tune them to the on-site situation. Next question, whether the voltage step in laboratory test is more than 20 volt or not. This voltage step can be 5 volt, can be 7 volt, can be 10, can be 20 volt. This depends on the sensor, on the test setup, on the UHF PD instrument. There is not a fixed value available because the design of couplers and so on, this is always different. So you have to check and you have to do the step 1 in a proper way. And from doing that, you will get the correct voltage step. There is no defined value which need to be taken for these tests. And if you are not sure if everything is running well for the sensitivity verification check number 1, send me the test reports. I will check them and will reply to you if everything is fine or if there are some mistakes in the reports. Any recommendation for better option to use frequency or time domain for getting pulse value in lab? Yeah, so we have 2 possibilities. Some people and experts are focusing more to the frequency domain. I'm trained and I really like to do it with the time domain, so with the PRPD pulses. For me, it's more helpful to do it in time domain with PRPD signals. So another question. Whether calibration and frequency response report of PD couplers also to be required from the manufacturers. Of course, this depends on your contract. Sometimes you buy the GIS with coupler and with PDM system at one manufacturer. And for that case, it's quite clear that you have to get the report about the combination GIS, sensor and PDM system. If you have a GIS with couplers and you are doing a kind of retrofit of PDM system, then you have to negotiate with GIS manufacturer that they apply, let's say, your PDM system on their laboratory to find the correct result. Oh, a lot of questions. That's great. Noise signals, we discussed this already. Then is another question. During laboratory tests, the GIS manufacturer generally performed the test on a straight GIB with one partition between 2 sensors, but practically at site, the GIS include many band switching devices and so on. How this will be taken care during laboratory test. The interesting point is that the UHF signal from the PD is attenuated in the same way as the artificial signal. So if you have between the 2 couplers in the laboratory test a band or a switching device, this is influencing both signals. At the end of the day, you will find the same voltage level for the artificial pulse. Next question. The PD can happen due any of the defects. So in that case, how can we calculate the number of sensors from defect itself? No, that's a misunderstanding. Maybe I didn't explain it in the correct way. You have to locate the sensors based on your rules of thumb. Maybe each manufacturer has knowledge about that. The utility, the user should tell him, I want to detect the protrusion or the moving particle only with 5 PC, and then the manufacturer will place the sensors on the correct location. I hope so. I hope so. But sometimes there are surprises. Next question, how we have to decide whether external filters are required or not. That's very simple. If you detect noise signals from outside and you cannot suppress them with some digital filters, then the only way is to use external noise filters which are mounted between sensor and the converter unit. So sometimes this happens because it's always difficult to handle all the noise signals. If you want to do a proper job, you are doing a frequency scan before you write the specification for the project. And to tell the PDM manufacturer about the noise signals and noise frequencies before he offers his system. Because then he can tune, he can adapt his system to the noisy situation on site. Next question, I think it's question number 12 or 15, yeah? When pulse magnitude injected from pulse generator, example 10 volt, to one sensor and the same is measured at then is said to be converted. In this condition, can you elaborate what should be percentage of the percentage of the measured signal? This is always under discussion. According to C. Gray, the percentage of the measured signal is not important. The only case is that you are able to detect it. But of course, it is more convenient if you have a percentage of measured signal, maybe of 10 or 20 or 25%, to really see the PD signals and to have a better basis for PD identification. But there is no value given by C. Gray. Next question. If suppose at site during PD test, the GIS manufacturer provide different make and model of PDM system rather than using the same model of PD monitoring system used at factory test, is it acceptable or not? If it is a better system with better sensitivity, this is welcome. The manufacturer should not change the technology of the system from frequency domain to time domain. And it is really a recommendation from SIGRE, use the same equipment from same manufacturer with same technology at step 2 as you used in step 1. This is really a strong recommendation. Otherwise, you have always a bad feeling if the measurements on site are correct and if the results are true. Next one. If we use filters, there are changes that activate PD signals will also be filtered out. It depends on the kind of filter. If you really have high pass or low pass filter, you really can really blind the PDM signal. So when you use the filters, you have to do the sensitivity checks, step 2, and if you can see the injected signal, then the filters are okay. Otherwise, the filters need to be cancelled. Next question. Online continuous PD measurement device is not recommended or not? Online continuous PD measurement. It depends on Yeah, it depends on many factors. So, for example, if you have, let's say, a GIS where you have the information or you have the knowledge that the quality is not so high, then online monitoring system is recommended, definitely. If you want to be sure that everything with the dielectric system is okay, then you have apply a continuous monitoring system. So, but it is also true that a high number of GIS, 400 kV level, for example, here in Europe, is tested with the UHF method during commissioning, but not monitored in service. And the argument of the utility is that they bought a high quality GIS where they expect that there are no failures, and by using the UHF method during commissioning, they cancelled all critical defects. And then there is no further need for a continuous PDM system. But if you ask me personally, I am a big friend of partial discharge monitoring systems. When I have such a system at my GIS, I always know the situation of the dielectric system, and some or many failures can be prevented. Next question, can we establish a sum rule as per the type of PD for selection of position of sensors? E.g., we did sensitivity analysis based on protrusion type of GIS. Will it be useful for particles? Yes, that's true. That was what I like to mention to you. If you go for the sensitivity detection for protrusions, that will cover also the required sensitivity for particles, but not vice versa. So if you go for protrusions, that's a very good way. Next one. We have faced many cases that the flashover occurs inside a working GIS, so nothing was detected on online PDMs. What can be the probable cause that partial discharge was not detected? Yeah, this situation can happen. There are, let's say, two possibilities. One possibility is that the flashover, the breakdown, happened immediately. For example, a particle is falling out from a shielding, then you have no time for the PD detection before breakdown, because everything happened in, let's say, 1 second. The second point is that you maybe have an online PDM system that is not sensitive enough. And that's the reason why these checks with sensitivity according to SIGRE is so important. Yeah. And please let me find an email with a proper description of that particular case. I will check and will give you an answer and my recommendation to your problem. Right, that was the last question, gentlemen, ladies and gentlemen. It's really my pleasure to answer your questions.
Thank you so much, Dr. Fischler. On behalf of all the participants, I would like to thank you for taking all the queries one by one and answering them with the best of your expertise. Now, shall we wrap up, sir?
I just have one thank you, and I'm VP Muni this side.
Yes, sir. Muni, sir, good evening.
Thank you all participants. I would like to thank you, Dr. Sadler, for delivering the wonderful tutorial, online tutorial for the benefit of all the participants. And because of some technical issues, I could not attend the meeting. Although I could listen, but I could not participate. Now I thank you, Dr. Sadler, for a wonderful lecture. And I hope the highwood engineering community world over benefit from his vast experience in career highwood engineering, and especially in the area of GIS. And I also request all participants, those who are interested to be member of SCD1 committee, Indian National Committee, they can give names and address to Mr. Bishan Datta or to me, so that we can include name, so that we can have regular meeting or have some program for additional information related to SCD1 committee topics. So thank you all. Switch over our organizers, please. Please take over. Thank you,
Thank
Dr.
you so
Sisler.
much, Mani sir. Now, so Dr. Schussler, shall we end?
Yeah, thank you very much. It was my pleasure to help this tutorial for India National Study Committee D1. I was really very positive surprised by so many participants and by the high quality of the questions. So it was really a pleasure for me. Thank you very much. I wish you all the best and please stay healthy. That's also very important.
Thank you so much, sir. Now it is a time to thank everybody who has contributed both by participating and academic sharing. The deliberations were applicable, and I wish these discussions to go a long way for the knowledge enhancement of participants and indirectly to the industry. I would like to thank all the participants for their curiosity and active participation in this program. The number of questions Dr. Sisler had to deal with clearly showed your interest in the program. Now I would like to thank Shri A.K. Bhatnagar, Director CBIP SIGRE India, and Shri B.P. Muni, National Representative on Steering Committee D1 and General Manager BHEL for taking time from their busy schedules for this program. My special thanks to our key speaker, Dr. V. Sischler from Germany, who took this event for the representatives from India. Now, to all the participants, I would like to announce that as Dr. Muni sir said, that kindly consider becoming member of SIGRE. The details of SIGRE with brochure have already or will be shared with you in your registered email IDs. You can look into it and consider becoming the member of SIGRE. To save your precious time, I am acknowledging all the member of the team who were involved in making this program successful. Thank you so much for joining with us. Thank you, Dr. Sisler. Thank you, Muni sir. Thank you all the participants. We'll
Thank
seek
you
all
and
of your
goodbye.
support in the future programs also. Thank you all and take care. Bye-bye.